Extraneous Solutions. Our objectives here are to solve a radical equation and identify extraneous solutions, solve an equation with rational exponents, solve polynomial equations, and solve absolute value equations. The strategy for solving a radical equation. Number one, we isolate a radical expression to one side of the equal sign. If the radical is a square root, then square both sides of the equation. If it is a cube root, then raise both sides of the equation to the third power. Now, if a radical term still remains, you'll just repeat steps 1 and 2. Solve the resulting equation. Check solutions by substituting them into the original equation. Now we must be careful when solving radical equations. It's not unusual to find extraneous solutions, roots that are in fact not solutions to the equation. These solutions are not due to a mistake in the solving method, but they're resulting from the process of raising both sides of an equation to a power. The following example demonstrates this phenomenon. Let's solve the square root of x equals -2. My strategy says to isolate the radical to one side. That's done. To square root, so to undo the square root, we're going to square both sides. So I'm squaring the left side and squaring the right side. Then I have x equals 4. All seems well until I check. When I check, I have the square root of 4 equals -2, and we know that is not true. Since, in this case, this is the only solution we came upon, we have to throw that solution out. We say no solution, as well as marking out the equal sign. Now let's practice solving some more involved radical equations. Solve the square root of 2x plus 1 equals 5. Step number 1, isolate the radical, is already finished. Now we're going to square both sides of the equation so that we can undo the square root. The square root of 2x plus 1 squared gives us 2x plus 1. 5 squared is 25. Now we have a simple linear equation to solve. I'll subtract 1 from both sides and divide by 2. We think that this is a solution, but we do need to check. Remember, this check is not to see if you've made a mistake, but to see if the solution that you came up with is actually a solution or not. So this is the square root of 24 plus 1 equals 5. That's the square root of 25 equals 5. And 5 does equal 5. So this is our solution. Always a good idea to come back and put a box around your answer. Solve the square root of x plus 60 equals x plus 4. We want to square both sides. Now be careful here. You're squaring the entire left side, and you have to square the entire right side, which means you're going to need to put parentheses around the x plus 4. The square root of x plus 60 squared will give us x plus 60, and x plus 4 quantity squared is x squared plus 8x plus 16. Now we have gotten rid of the square root, but we have a quadratic equation. Our strategy here is to go ahead and get everything on one side equal to 0. So I'm going to subtract x from both sides and 60 from both sides. This will give me a 0 equals x squared plus 7x minus 44. Now I can factor 0 equals x times x gives me my x squared. If I have a positive 11 and a negative 4, those will multiply together to give my negative 44 and add together to be the 7x that I need in the middle. Now, the principle of zero products or zero product rule says that we set each of those factors equal to 0, and so x is negative 11 and x is 4. Now, it looks like we have two equations, but we need to check them. And yes, we have to check both of them. It could be the case that both work, could be that one works and the other doesn't, or it could be that neither one of them works. So we do have to follow through with checking each one. Let's try the negative 11 first. This is going to be the square root of 49 equals a negative 7. And now the square root of 49 is 7. That does not equal negative 7. So that means x cannot equal negative 11. Let's check x equals 4. So that would be square root of 4 plus 60 equals 4 plus 4. This is the square root of 64 equals 8. The square root of 64 is 8, and 8 equals 8, so we're good. We have x equals 4 as a single solution to this equation. In this next example, we have two radicals. Our first step is to isolate a radical on one side. That means we want just a single radical on the side. So I'm going to go ahead and add the square root of x minus 12 to both sides. And then the next step is to square both sides. Square the left, square the right. Squaring the square root of x gives me x, and on the right side you have to see this as a binomial. So I'm squaring 2. I'm multiplying those terms together and doubling them. That makes a 4 square root of x minus 12. And then my square root of x minus 12 squared is going to be x minus 12. All right, so we have a case where we've squared both sides of the equation and there's still a radical. So we have to redo steps 1 and 2. So step 1 is to isolate the radical. We're going to isolate the square root of x minus 12. So if I subtract x from both sides, that'll go away. 4 and negative 12 is a negative 8. So I'm going to add 8 to both sides. That gives me 8 equals 4 square roots of x minus 12. Then I'll divide both sides by 4 because, again, I want the radical expression by itself. That 4 is simply a coefficient. So I'm dividing both sides by 4. That gives me 2 equals the square root of x minus 12. Okay, now our radical is completely isolated. So we'll go ahead and square both sides again. This gives me 4 equals x minus 12. Simple linear equation. We'll go ahead and add 12 to both sides and I get x equals 16. Don't forget, we need to check. This could be an extraneous solution. The square root of 16 minus the square root of 16 minus 12 equals 2. So the square root of 16 is 4 minus 16 minus 12 is 4, and the square root of 4 is 2 equals 2. 2 equals 2 is true. So x equals 16 is our solution. Here we have a cube root. The cube root of x minus 5 equals 2. Since we have a cube root, the way to undo that is to cube both sides. That gives me x minus 5 equals 8. And x equals 13 after I add 5 to both sides. Now, you're never going to have an extraneous solution if you have to cube both sides of your equation. But if you want just to set your mind at ease, you can check. The cube root of 13 minus 5 equals 2. The cube root of 8 is 2, and that is indeed true. So we have x equals 13 as our solution. Here we have some equations with rational exponents. Now, rational exponents are exponents that are fractions, where the numerator is a power and the denominator is a root. For example, these are equivalent. 8 to the 2/3 can be written as the cube root of 8 squared. It could also be written as the cube root of 8 squared, and it simplifies to be 4. We can solve equations in which a variable is raised to a rational exponent by raising both sides of the equation to the reciprocal of that exponent. Doing this will eliminate the exponent from the variable term, since a number multiplied by its reciprocal equals 1. For example, 2/5 times 5/2 equals 1. Let's solve this equation. X minus 5 to the 3/2 equals 8. So I'm going to rewrite x minus 5 to the 3/2, leave a little space, equals 8. The reciprocal of 3/2 is 2/3. So if I can take this and raise it to the 2/3 power, and remember I'll need to do that for both sides. When you raise a power to a power, you multiply the exponents. And I know that 3/2 times 2/3 is going to equal 1. That frees up my x minus 5. Now, 8 to the 2/3, we can come to the side and calculate if we need to. We can write this as the cube root of 8 squared. I know the cube root of 8 is 2, and 2 squared is 4. So x minus 5 is 4. Adding 5 to both sides, I get 9. I do need to check. So putting my answer into the original equation, we'll see if we get a true statement. 9 minus 5 is 4 to the 3/2 is 8. The square root of 4 cubed is 8. The square root of 4 is 2. Cubed is 8, and I know 2 cubed is 8. So x equals 9 is our solution. Let's run through a few definitions here. A polynomial. A polynomial of degree n is an expression of the type a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus etc. plus a sub 2 x squared plus a sub 1 x to the 1 plus a sub 0, where n is a positive integer and a sub n through a sub o are real numbers and a sub n is not equal to 0. Setting this polynomial equal to 0 gives a polynomial equation. The total number of solutions, real and complex, to a polynomial equation is equal to the highest exponent n. Now, our focus in this section with polynomials will be rational expressions. A rational expression is a fraction where the numerator and denominator are polynomials. Solving rational equations. When solving a rational equation, our goal is to perform algebraic operations so that the variables appear in the numerator only. We will eliminate all denominators by multiplying both sides of the equation by the least common denominator. Just a note, a solution to a rational equation is extraneous if it makes a denominator 0. Let's solve 3 over x squared minus 44 over x equals 15. In this equation, I can see that I have fractions because I'm dividing by x and by x squared. The least common denominator of x and x squared will be x squared. So what I'm going to do is multiply both sides of the equation by x squared. The right side and the entire left side as well by x squared. Okay, when we distribute, x squared times 3 divided by x squared will give us just 3. Minus x squared times 44 divided by x will give us 44x equals 15x squared. All right, now I have a quadratic equation. So it's my job to go ahead and get this all on one side. I'm going to add 44x to both sides and subtract 3, and that leaves me with a 0 on the one side. Let's see if we can factor this. So we'll have 0 equals my 15x squared. Let's break it up as 15x and x. My negative 3, we can break that up as a negative 1 plus 3. Again, use whatever factoring strategy you're used to. And that gives me a 45x minus 1x is a positive 44x for the middle. And then we can solve these simpler linear equations. So for this one, 15x equals 1 and x equals 1/15. Over here, x equals negative 3. Now neither one of those are going to cause us to have division by 0. So we have two valid solutions. Now let's solve 12 over x squared minus 4 minus 3 over x minus 2 equals 9 over x plus 2. It's a good idea when you have something that can be factored and a denominator that you go ahead and factor it to see what it's made of. Sure makes it a lot easier to figure out what the LCD is. I'm looking at denominators of both x plus 2, x minus 2, x minus 2, and x plus 2. So the LCD is going to be x plus 2, x minus 2. I'm going to multiply the left side by x plus 2, x minus 2, and the right side by x plus 2, x minus 2. Now, when this multiplies through, we're multiplying both of those to this fraction and both of those to this fraction. When I multiply it by that first fraction, both the x plus 2 and the x minus 2 will remove, and we have 12. When I'm multiplying it by the second fraction, the x minus 2's are removed, and I have a minus 3 times x plus 2. On the right hand side, my x plus 2's are removed, and I have a 9 times x minus 2. So this is 12 minus 3x minus 6 equals 9x minus 18. We have a simple linear equation that we need to solve, so I'm going to add 3x to both sides. I know that 12 and negative 6 is 6, When I add 18, I get 24. Dividing both sides by 12, I get x equals 2. Now, it seems like all is well and good, except that if I would actually use 2 in our denominator, it causes this fraction to have a 0 denominator and this fraction to have a 0 denominator, so we can't actually use that. And since this was the only solution that we came upon, we're going to have to say that this has no solution. Absolute value equations. Now, absolute value can be thought of as distance from 0. So if we look at a statement like absolute value of x equals 5, it follows that x must have a value without the absolute. It must have a value of 5 or negative 5. Isn't this correct? Because the absolute value of 5 equals 5, or the absolute value of negative 5 equals 5. And we're looking for all solutions where the absolute value of that number would be 5. In other terms, thinking of this as a distance, if x is a distance of 5 from 0, x could be sitting at 5 or at negative 5 on our number line. When solving absolute value equations, like many of the other things we've been doing, we must make sure to isolate the absolute value before applying the definition of the absolute value. It's also essential to check your answers as a final step. Let's solve these two absolute value equations. The first one, absolute value of x equals 3. This means that x must have a value of 3, or x must have a value of negative 3 for us to have taken the absolute value of x and gotten 3. If we wanted to check this, we put that in as absolute value of 3 equals 3, and this is true. The absolute value of negative 3 equals 3, and this is true. So both of our solutions are correct. In the next example, we have the absolute value of x is negative 3. Now this doesn't quite make sense because we're thinking of the absolute value as a distance. So this is saying the distance that x is away from 0 is negative 3. And distances cannot be negative. However, some students like to go ahead and solve this and say we remove the absolute value and just replace with opposite signs on our answer. So, do we really have values of x equals negative 3 or x equals 3 as our solution? Let's check and see. The absolute value of negative 3 equals negative 3. Well, the absolute value of negative 3 is positive 3, and then it's no longer equal to negative 3. So that is not correct. Let's try 3. The absolute value of positive 3 is equal to negative 3. This means 3 equals negative 3. We know that's not correct either. Neither of these are correct because the initial statement was not correct. The absolute value of a number cannot be a negative number. For this one, we'll have to say no solution. Let's practice a few of these solving absolute value equations. In this problem, I have the absolute value of 2x plus 5 minus 1 equals 6. Our first step is to isolate the absolute value. So the absolute value of 2x plus 5 equals 7 after adding 1 to both sides. Now it doesn't matter what is inside the absolute value. We're saying that the absolute value of that thing is 7. So the value inside of that must be 7 or negative 7. And what was that thing? That thing was 2x plus 5. Again, the absolute value of this is 7. So the value, without absolute value signs, the value of it must be 7 or negative 7 for us to have taken the absolute value of it and gotten a 7. Now we have two simple linear equations that we can solve. 2x equals 2 and x equals 1. 2x equals negative 12 and x equals negative 6. All right, you can visually check these. 2 times 1 is 2, plus 5 is 7. Absolute value of 7 is 7, minus 1 is 6. So we know x equals 1 works, and now we can check x equals negative 6. Putting negative 6 into my original equation, I have negative 12 plus 5 is negative 7. Negative 7, absolute value is 7. 7 minus 1 is 6. Both of our solutions are going to work for us. In this example, we have 5 minus 3 times the absolute value of 2x plus 1 equals negative 4. Again, we want to isolate the absolute value expression. Now, a caution here, some students will look at this and get excited and say, well, 5 minus 3 is 2, but this 3 is connected to this absolute value by multiplication, so you can't combine the 5 and the minus 3. Okay, so what you need to do is subtract 5 from both sides first. So we'll have a negative 3, absolute value of 2x plus 1 equals negative 9 after subtracting 5 from both sides. Now, this negative 3 that's in front is not a part of the absolute value expression, so we need to divide it off. Once we do that, we have 2x plus 1 in absolute values on the left side, and on the right side we have 3. Now remember, we are saying the absolute value of 2x plus 1 is 3. That must mean that that expression inside must have been a 3 or a negative 3 for the absolute value of it to be 3. So I know that 2x plus 1 either equals 3 or 2x plus 1 can equal negative 3. And then we solve those simpler linear equations. We get x equals 1 and x equals negative 2. Again, you can visually check this and you'll see that both of those solutions work.